Hello everyone, and welcome back to Math 220A Mathematical Logic, Lecture 25, the number of countable models. Throughout our discussion today, T will be a complete theory in a countable language, and so that T has infinite models. To rule out, as usual, the trivial case. Definition: for any infinite cardinal kappa, we let I of T kappa be the number of non-isomorphic models of T of cardinality kappa. Of course, we know by the upwards and the downwards Leeuwenheim-Skolem theorems that if T has infinite models, then the number of models of T of size kappa is greater or equal than 1 for any kappa, and it's less or equal than 2 to the kappa. Once again, simply because to specify a model of size kappa, we have to specify the interpretations of all the symbols, the function, the relation, and the constant symbols. And a simple calculation shows that there are at most 2 to the kappa many choices for those, since the language is assumed to be countable. So we see that this function takes values in this range for any kappa. Now, definition, we say that T is kappa categorical if it has only one model of cardinality kappa up to isomorphism. Today we will discuss the possible values of the function I t of aleph naught. So we're asking for the possible numbers of countable models of a given theory. A couple of examples. One, we have already seen that the theory of dense linear orders without endpoints, DLO, has exactly one countable model. The isomorphism between any two can always be built by back and forth using the density assumption. 2. For each natural number n greater or equal than 3, there exists a theory Tn with the number of countable models of Tn up to isomorphism exactly n. To get an example with exactly 3 non-isomorphic countable models, we can take the language to consist of the order and countably many constant symbols, C0, C1, etc. And we consider the theory T3 to be the theory of dense linear orders, together with sentences asserting that Ci is less than J for all I less than J natural numbers. Then T3 has exactly 3 countable models up to isomorphism. How are these models distinguished? Well, the possibilities are that the sequence C0, C1, C2, etc. has an upper bound So the first possibility that it doesn't in the given model, the second possibility that it has an upper bound, but no least upper bound. And the third possibility that it has a least upper bound. It's not hard to check that all three of these models are not isomorphic, pairwise non-isomorphic, and any other model has to be isomorphic to one of them. Now, to get more than three models, this example can be iterated. We can let L4 be L3 together with a new unary predicate symbol. And then we can take T4 to be T3 together with sentences expressing that the set of realizations of P is dense-codense in the ordering. Then T4 is complete and has exactly 4 countable models. Now, depending on whether C has least upper bound inside the predicate or it doesn't have it inside the predicate. So this adds one more option to T3. And this idea can be iterated to get a theory with exactly n models for any n greater or equal than 3. Third example, we can consider the theory of algebraically closed fields of positive characteristic P. And then the number of countable models is exactly Aleph naught. This follows from a basic algebraic fact that two algebraically closed fields are isomorphic if and only if they have the same transcendence degree and the same characteristic, of course. But here, since the prime field is just Fp, the field on finitely many elements, the transcendence degree, there are countably many options for the transcendence degree. It can be any finite number or infinite. So altogether we have countably many possibilities. And let's consider one more example. For number of countable models of RCF is the same as the number of countable models of true arithmetic is equal to 2 to the Aleph naught, the maximal possible number of models. Looking at these examples, we see two obvious missing questions. So question 1, can we have that the number of countable models of T is equal to 2 for some theory T? And question 2, can we have that the number of countable models of T is strictly between Aleph naught and continuum? Of course, if the continuum hypothesis is true, then the second question has a trivial negative answer. Watt conjectured that the answer is negative even without the continuum hypothesis assumption, so even in those models of set theory where the continuum hypothesis fails. This remains one of the deep open questions of model theory, which also has deep connections to recursion theory and set theory and descriptive set theory. Watt's conjecture. The best known general result here is the theorem of Morley, which says that if the number of models, countable models of T, is greater than Aleph 1, then it is already continuum. So the only possibility for the intermediate value is Aleph 1. Now Morley's theorem uses some results from descriptive set theory, which we are not going to develop here. Another known special case of Watt's conjecture is due to Shelach. It shows that Watt's conjecture holds for Aleph not stable theories. This is a difficult theorem using deep tools of stability theory that we don't have time to develop in this course. And like I said, the general case of the Watt's conjecture is completely open. On the other hand, the first question, if we can have exactly two countable models, is surprisingly answered. It's a theorem of Watt, which shows that it is not possible to have exactly two countable models up to isomorphism. It's a somewhat surprisingly sounding fact. We'll prove it, but before we can do it, we have to develop some additional tools and deeper understanding of countably categorical theories. So those which have exactly one countable model. Towards this purpose, we have the following characterization of countable categoricity in terms of the space of types in particular. This theorem was proved independently by Ryll-Nardzewski, Engler, and Svenonius. The following are equivalent. 1. T is Aleph not categorical. 2. Every type in Sn of T is isolated for all n greater or equal than 1. 3. The cardinality of the space of types of T is finite for all n less than omega. And 4. For each n less than omega, there exists a finite list of formulas phi 1 of v1 through vn through phi m of v1 through vm, all formulas in L without parameters, such that every formula psi of v1 through vn in the same number of free variables n satisfies that in T phi I of v bar is equivalent to psi of v bar for some I less or equal than m. In other words, there are only finitely many inequivalent formulas in any given fixed number of free variables. Proof. 1 implies 2. Assume that P is an n-type in T, which is not isolated, then there exists a countable model M of T omitting P. Here we're using the omitting types theorem. On the other hand, there is also a countable model N of T which realizes P. So we know that every type can be realized in some model of T, but then using downwards Leeuwenheim-Skolem theorem, we can find a countable model of T still containing the realization of this type in some potentially bigger model. So this is how we get it. But then, clearly, M cannot be isomorphic to N because the isomorphism would send a realization of P to another realization of P. All formulas would be preserved by an isomorphism, so it's impossible. So T is not Aleph not categorical in this case. So this shows the implication 1 implies 2. Next we show that 2 implies 3. Suppose that the set of types Sn of t is infinite for some given n. Now for each type p in Sn of t, we let phi p be a formula which isolates p. And since we assume in 2 such a formula exists, every type is isolated. But because we have that the union of the basic Klopen sets phi p, where p varies over all types in Sn of t, is the whole space of types, because every type belongs, p belongs to the Klopen set for the formula phi p, which isolates p, but in particular it belongs to p. So we have that the whole space of types can be covered by such sets, and of course the space of types is compact, and the sets are Klopen. There has to be a finite subcovering, so there exist some types p1 through pm, finitely many, in Sn of t, such that the corresponding sets phi p1 union phi pm already give a subcovering of the whole space of types, so the union is the whole space of types, but also by the choice of the formulas phi p, we know that phi p is the set consisting of a single point, the type p, because phi p isolates p. So we see that the space of types Sn of t has cardinality less or equal than m, so in particular it is finite. This proves 3. Next we show that 3 implies 4. So fix n and suppose that the space of n types is finite. So for example it's given by p1 through pm for some m less than omega. Then we can choose some formula theta I in pi such that we also have that the negation of theta I belongs to pj for all I different from j. So namely we know that any two types pi and pj are distinct, so there must be some formula which belongs to pi but not to pj. Then for a fixed I we can choose such a formula for every other j and take their conjunction. Then it will belong to pi but to neither of the types pj. And we repeat this choice for each type in our finite set. But then it follows that theta I isolates pi because it's the only type belonging to the Klopen set corresponding to the formula theta I. And also for any formula psi of v1 through vn, we have that t implies psi of v bar is equivalent to the disjunction of the formulas theta I for over all I such that psi belongs to pi. Thus, each psi with free variables v1 through vn is equivalent to the formula given by the disjunction of the theta i's for I and s for some as a subset of 1 through m. So there are at most 2 to the m inequivalent formulas. In n free variables. This shows 4. Finally, we show that 4 implies 1. Let M be an arbitrary countable model of T if a bar is an n-tuple from M. We let S subscript a bar be the set of all those I less or equal M such that M satisfies phi I of a bar, where phi I is the finite set of formulas given by the assumption 4. So this is a list of all non-inequivalent formulas in n many variables. So given this, we then have that the type of a tuple a bar in M is isolated by the following conjunction. So we take the conjunction over all I in S a bar, phi I of V bar, and we take the conjunction over all I not in S a bar, the negation of phi I of V bar. And since by assumption every formula is equivalent to one of the phi i's, this shows that the type is indeed isolated by specifying the truth values for each of the phi i's. Thus, since a bar was an arbitrary tuple in our model, and this condition holds for every n by assumption, so for every number of free variables, hence for every length of a finite tuple a bar, we see that M is atomic. Hence, by a result we have proved earlier, M is prime. So M is a countable prime model, and we know that prime models are unique up to isomorphism. And M was an arbitrary countable model of T. We conclude that all countable models of T are isomorphic. So this shows that T is Aleph not categorical and concludes the proof of the theorem. This theorem, this characterization, it gives us a lot of information about definability in Aleph not categorical theories, which we will return to soon. But for now, let us move on and start working towards the proof of the Watts result, that it's impossible to have exactly two countable models up to isomorphism. First of all, we will need the following lemma. Assume that kappa is an infinite cardinal, and let A be a subset of parameters in M with the cardinality strictly less than kappa. Let us define the structure M subscript A to be the LA structure obtained from M by interpreting the new constant symbols in A by the corresponding elements of A. So every element of the set capital A is named by a new constant symbol. Then, if M itself is kappa saturated, then MA is also kappa saturated. Proof. Assume that B is a subset of the structure MA, so that the cardinality of B is strictly less than kappa, and assume we have a one type P in S1 of B in the structure MA. But then note that every formula in P is of the form phi of x A bar B bar for some A bar, a finite tuple from A, because it is an LA formula, and B bar, a tuple from B. In other words, we see that P is a partial type over A union B in the sense of the structure M, and of course this is still consistent with the B theory of M, because it was consistent with the B theory of MA, which is an expansion of M. So we can think about P, we can identify P with a one type over A union B in the sense of M. And of course, the cardinality of A union B is still strictly less than kappa by our assumption on A and B. So it follows that P viewed as a one type over AB in the sense of M is realized in M by the assumption of kappa saturation of M. But then again we check that this realization gives a realization of P, of the original type P, in the sense of the structure MA. So this straightforward observation indeed verifies the lemma. And now we can prove the celebrated theorem of Watt that says that the number of countable models cannot be equal to 2 for any theory T. Proof. The proof combines a lot of the results that we have developed up to now. Suppose, towards a contradiction, that we have some theory T with exactly 2 countable models. In particular, we have that T has strictly less than 2 to the aleph naught many countable models there exists n a prime model of T and also M a countable saturated model of T. And so we have that M is an elementary extension of N, because N is prime, so it has an elementary embedding into every model, in particular into M. But now, since the number of models is 2 and not 1, we have that T is not aleph naught categorical, by the theorem that we have just proved, the characterization of aleph naught categoricity, there exists a non-isolated type P in Sn of T for some n less than omega. Because by the previous theorem, all n types in a countable categorical theory are isolated for every n. Okay, so we can find some type P like this. Next, we let A bar be an element of the saturated model M, or rather an n tuple in the saturated model M, realizing P. So we know that there has to exist some tuple realizing P, because it is a type of the empty set, and M is a countably saturated model. Next, we let T star be the LA bar theory of the structure MA bar, i.e. The expansion of M by naming all elements of the tuple A bar by new constant symbols in the notation of the previous lemma. By the Ryll-Nardzewski theorem, again, we know that there are infinitely many L formulas in the free variables v1 through vn, which are all pairwise inequivalent in T. So here we use that, we already know that T is not aleph naught categorical, hence for some n, so namely the same n for which we have an isolated type, there are infinitely many L formulas in the variables, in n free variables, which are pairwise inequivalent with respect to T. Note that as they are still T star inequivalent, because T star is an expansion of T and T is already says that they're inequivalent, it follows that T star is also not aleph naught categorical as a theory in the expanded language LA bar. But by the previous lemma, we have that M subscript A bar is a saturated LA bar structure. So here we use that M was a saturated L structure, a countable saturated LA structure, and A bar is a finite tuple. So in the expansion we only naming by constant symbols some finite set, so a set smaller than the saturation cardinal of the structure M. Hence by the previous lemma this expansion remains saturated in the expanded language LA bar, excuse me. But now we again use that every theory in a countable language with a countable saturated model has also a prime model. And this applies to our situation, so it follows that T star has a prime model. So it's some structure in the language LA bar which is prime for the theory T star. Now we also know that, okay, let's denote this prime model, let's say by A. We also know that every prime model of a countable theory is in particular countable and atomic. Model of T star. Now let B denote the L reduct of A. So you're forgetting the interpretations for the constants in the tuple A bar. Since we have that A realizes T star, B contains a realization of P. Namely, since T star was the complete theory of the structure MA bar, it contains all sentences expressing that for every formula from the type P, which is an L formula, excuse me, that the constants in A bar satisfy this formula. So hence, in the model A model of T star, we still have that the interpretation of those constants satisfies every formula from P, and hence the interpretation of these constants, which is just a tuple in B, gives us a realization of P. But then we have that B is not isomorphic to N, because N is a prime model and P was non-isolated, so N doesn't realize P, but B is a model of T which realizes P, so they cannot be isomorphic. On the other hand, because T star is not Aleph not categorical, as we have already observed, applying the Ryll-Nardzewski theorem again, there is a non-isolated LA bar type, well, N type for some finite N, possibly different from the one we had for P. But then this type is not realized in A, because A is a prime model of T star, and hence a non-isolated LA type in the sense of T star is not realized in it. Thus A is not saturated as a model of T star But now, if the structure B were a saturated L structure, then by the previous lemma, A would also be saturated, because A is an expansion of B by naming finitely many symbols by constants. Thus it follows that B is not isomorphic to M, because M is a saturated model of T, but we just observed that B is not saturated. So combining, we have M, a saturated model of T, N, a prime model of T, and we have just obtained B, an intermediate structure, which is, of course, an elementary extension of N, and is an elementary substructure of M, because M is universal as a saturated structure, but it's not isomorphic to any of them. Hence, we have found at least 3 non-isomorphic models, countable models of T. This concludes the proof of Watt's theorem. Let us conclude our discussion today by observing another corollary of the Ryll-Nardzewski theorem for Aleph-Node categorical theories, which establishes a strong form of local finiteness for such structures with respect to the algebraic closure operator in them. So suppose that T is Aleph-Node categorical, then there is a function f from the natural numbers to the natural numbers, such that if M is an arbitrary model of T, A is a subset of M, and the cardinality of A is less or equal than N, then the cardinality of the algebraic closure of A in M is less or equal than f of n. So in particular, the algebraic closure of a finite set is finite, a property which doesn't have to hold in general. Proof. By the Ryll-Nardzewski theorem, we have that ST is Aleph-Node categorical. The cardinality of the space of n plus 1 types in T is finite. Since it's finite for any number of free variables, so in particular for n plus 1. Now let Q1 through Qk list all n plus 1 types in this set, so there are finitely many, so K is the cardinality of the space of types. And we also consider the set X to consist of all I between 1 and K, such that Qi contains a formula phi of V W bar such that M satisfies for all V0 through V capital N, we have that the conjunction over all I from 0 to capital N phi of Vi W bar implies the disjunction over all I less than j less or equal than capital N, Vi is equal to Vj, and so that this holds for some capital N. And also for I an element in X, meaning that there exists such N, we can let Ni be the least N such that for some formula phi of VW bar, we have that for all V0 through Vn, the conjunction overall phi of Vi W bar over I from 0 to n implies the disjunction Vi equals to Vj overall I less than j less or equal than capital N is in Qi. So since we know that for each I in X, the corresponding type contains such a formula for some n, will let Ni be the minimal capital N for which such formula belongs to Qi. Now, if we are given A, B1 through Bn, arbitrary elements in M, a model of T, and if we have that A is algebraic over B bar, so more precisely over the elements, the set of elements appearing in this tuple B bar, then the tuple A, comma B bar realizes some Qi with I in X. Because for A being in the algebraic closure of B bar, there must be some formula phi of VW bar which witnesses that. So it has only finitely many realizations, finitely many choices for the V variable when W is fixed. So we can pick a formula like that. Okay, so then we see that this realizes some Qi with I in X, and then the cardinality of the set of all X in M such that the tuple XB bar realizes Qi is going to be less or equal than capital N I, because this was chosen to be the minimal one which satisfies it. Thus, we have that the cardinality of the algebraic closure of the tuple B1 through Bn is less or equal than the sum over all I in X and I. This holds because the element A was of course arbitrary, and so we can just take f of n to be the sum over all I in X and I. And this provides the desired bound on the cardinality of the algebraic closure of a given tuple of length n. This concludes the proof of the corollary.